Hello, this is Yashwin. In this video, I'll be solving paper 4 variant 2 May-June 2020 0625 physics. Starting with question number 1, figure 1.1 shows the speed time graph of a person on a journey. On the journey, he walks, then waits for a bus. He then travels by the bus. He gets off the bus and waits for 2 minutes. He then walks again. His journey takes 74 minutes. A, for the whole journey, calculate the distance traveled. So the distance in a speed time graph is the area under the graph, and so we can calculate the area of these three triangles, which would give the total distance. But first we need to convert the minutes over here to hours, since speed is given in kilometers per hour. And so this means we should first write speed is equal to area under the graph, which means area of the three rectangles. And so that is the height of the first rectangle, which is 5 multiplied by the time. 5 multiplied by the time, which is 20 minutes. I'll convert it to hours by dividing it with 60, plus the second bar, which has the height of 40 multiplied by 20 minutes, which I'll convert it to hours by dividing by 60, and the third bar, which is 6 into 22 minutes divided by 60. And so the sum of all of this is 17.2 kilometers. I'll round it to two significant figures, which is 17 kilometers. To the average speed. So the speed over here is going to be equal to total distance divided by the time taken. And so speed is equal to, I'll use the original value which of the distance which we got over here, which is 17.2, divided by the time taken, which is 1.2 kilometers, and that is 14 kilometers per hour. B, state and explain which feature of a speed time graph shows the acceleration. This is shown by the gradient, as it shows the change of speed divided by the change of time, which is basically what acceleration is. C, state and explain the acceleration of the person at 40 minutes. Alright, so at 40 minutes, the gradient does not change, which means the acceleration does not change either. And so its speed is constant. Speed is constant. So acceleration is 0. Figure 2.1 shows a train. The total mass of the train and its passengers is 750,000 kilograms. The train is traveling at a speed of 84 meters per second. The driver applies the brakes and the train takes 80 seconds to slow down to a speed of 42 meters per second. A, calculate the impulse applied to the train as it slows down. Impulse has the formula of force into time. Force into time is also equal to the change in momentum. Since we don't have a force into time over here, we'll simply calculate the change in momentum which occurs, and that would give the impulse as well. So I'll take m out of the bracket, which is a common value, which would mean the mass multiplied by change in velocity. Mass of the train is 750,000 kilograms, and change in velocity is from 84 meters per second to 42 meters per second, and that means 315,000 newtons per second. So I'll write it in standard form, rounding to two significant figures. 3.2 into 10 to the power of 7 newtons per second. B, calculate the average resultant force applied to the train as it slows down. So we have seconds over here, the time, and also the impulse. Now we can calculate force, which is equal to impulse divided by the time taken. and that is 3.2 into 10 to the power of 7 divided by 80, which is equal to 393,750, which is 3.9 into 10 to the power of 5 newtons. So over here I'm basically dividing not this actual 3.2 into 10 to the power of 7 by 80. I'm dividing this figure, which was the actual figure in the previous part, by 80. Though I might be writing the value which we had as the answer. C. Suggest how the shape of the train helps it to travel at high speeds. So as you can see over here, this is a streamlined figure, which means streamlined shape. So it doesn't have very many barriers or an area which would increase air resistance. So the streamlined figure decreases the air resistance, which means it helps traveling the train at higher speeds. D. The train took 80 seconds to reduce its speed from 84 meters per second to 48 meters per second. Explain why, with the same braking force, the train takes more than 80 seconds to reduce its speed from 40 meters per second to 0. I'm first going to be starting by writing the formula of force over here, which is change in momentum divided by time taken. So initially, the speed was decreasing from 84 meters per second, and in the second case, it is decreasing from 42 meters per second. 84 over here is greater than 42, and since the speed is higher, that means the air resistance for this speed is going to be much larger than the air resistance in second case. And since air resistance over here is greater, the force needed to oppose the air resistance in the first case is going to be greater. As you can see over here, force and time are inversely proportional. If force required is greater, time required would be less. In the second case, the speed is less, which means for air resistance would also be less, and so to oppose that air resistance, the force required is much less. Once again, since force and time are inversely proportional, in the second case, time required is going to be greater than the first case. So the answer is less air resistance for slower speed means greater time to stop. E. At A, the train travels a greater distance before it stops along the same track. The train has the same speed of 84 meters per second. Before the brakes are applied, suggest a reason for this. So water over here reduces the friction. Question 3a. A solar panel receives energy from the sun at a rate of 5 kilowatts. The thermal energy is transferred from solar panel to water with an efficiency of 20%. Cold water of mass 15 kg enters the solar panel every hour. The specific heat capacity of water is 4200 joules per kg degree Celsius. Calculate the temperature increase of the water. So the solar panel receives energy from the sun at a rate of 5 kilowatts. This means this is power input because this is receiving, the panel is receiving this power, and this over here is the efficiency, and then we have mass over here per panel every hour. This is the time. Every hour means 3600 seconds. We want them in the SI units, all of the values, and specific heat capacity is given over here. Calculate the temperature increase of water. Specific heat capacity is equal to energy over mass into change in temperature. So change in temperature is equal to energy divided by specific heat capacity into mass. Specific heat capacity and mass are given in the question, and now we need to figure out the energy over here. So energy is equal to power into time. Over here, this is the energy received by the water, which means the power obtained by the water, or power output, because this is going to be the power, or you can, in other words, you can also say useful power, because not all of the power received by the solar panels is going to be absorbed by the water. So over here, power output, which is the power of the water received by the water, divided by the total power input into 100, is equal to efficiency, which is 20%. So that means power output, which we need to calculate, is going to be equal to 20 multiplied by the power input, which was 5 kilowatts, and all of this divided by 100. So this gives the as power output as 1000 watts. And this power is going to be used to supply the energy to the water, which is energy is equal to power, which is 1000 watts multiplied by the time taken, and that is 1 every hour, which is 3600 seconds. And so this energy is equal to 3.6 into 10 to the power of 6 joules. So change in temperature here was equal to energy divided by specific heat capacity into mass. I'll start by writing over here since the space is not sufficient. 3.6 into 10 to the power of 6 divided by specific heat capacity, which is 4200, multiplied by the mass, which is 15. And so the change in temperature is going to be 57 degrees Celsius. B. State and explain one advantage and one disadvantage of heating the water in a solar panel compared with heating the water in a coal burning boiler. Alright. So the advantage is that since no fossil fuels are burned in the solar panel, no pollution or no carbon dioxide is produced in this method. And the explanation over here is the disadvantage is that since at night the sun is not available, that means at night time the powers are pretty much useless. Figure 4.1 shows a liquid in glass thermometer without a temperature scale. The liquid inside the thermometer has a melting point of negative 39 degrees Celsius. A describes simple experiments to mark the positions of fixed points, which are 0 and 100 degrees Celsius, on this liquid in glass thermometer. So these are a few points which you'll have to learn by heart, starting with the 0 degree Celsius, which is one of the two fixed points. Is you'll have to place the thermometer in melting crushed ice. So crushed ice ensures the exposure of thermometer to the melting ice, which has temperature of 0 degrees Celsius, and so it would be accurate reading which you'll be obtaining by this method. So after placing the thermometer in crushed melting ice, the thermometer would detect the temperature, which would be 0 degrees Celsius. And once you've placed it over there, the liquid would stop moving at 0 degrees Celsius, and then you can mark the lower fixed point. So the steam over here would have the temperature of 100 degrees Celsius, which is the upper fixed point, and then the liquid would stop moving after indicating 100 degrees Celsius, which would be the place you'd have to mark as upper fixed point. B. A scientist is measuring temperatures at the South Pole. These temperatures have a minimum value of negative 90 degrees Celsius. State why the liquid used in thermometer figure in figure 4.1 would not be suitable for this scientist. The question mentions over here, melting point is negative 39 degrees Celsius, which means freezing point is also negative 39 degrees Celsius, and this temperature is higher than the minimum value over here, which means at 90 degrees Celsius the liquid would already be solid, and so it cannot move and function as a liquid in glass thermometer. C. State a design change that 1 can increase the sensitivity of a liquid in glass thermometer. This can be attained by a thinner bore. 2. Increase the range of a liquid in glass thermometer. Over here, a longer tube would be useful. D. State the property of the liquid which ensures that scale on a liquid in glass thermometer is linear. This is attained by uniform expansion of the liquid, which means it expands equally for every change in temperature. 5. Figure 5.1 shows crests of a wave approaching a barrier where the wave is reflected. A. On figure 5.1, draw 3 crests of the reflected wave. I'll start by drawing the normals, which are 9 perpendicular to the barrier. We only need to draw 3 of them. So I'll draw 3 normals over here. These are the dotted lines which represent the normal, and I'll start by measuring the angle of incidence, which means the angle between normal and the incident wave. And this is an angle of 27 degrees, which means the reflected rays should also have an angle of 27 degrees. Alright, so this should be my angle of reflection. Here are my reflected rays. B. The wave has a wavelength of 36 centimeter and a speed of 1.2 meters per second. Calculate the frequency of the wave. So frequency is equal to speed over wavelength. Speed is in 1.2 meters per second, which means the wavelength should also be in meters. 36 centimeters is equal to 0.36 meters, which means speed 1.2 divided by wavelength 0.36 is equal to 3.3 hertz. C. Complete the following sentences. An echo is the name of a reflected dash wave, reflected sound wave. The waves that form an echo are a type of longitudinal waves. Okay, longitudinal waves are made up of dash and rarefactions. They are made of compressions and rarefactions. 6a figure 6.1 shows an arrangement of glass prism inside a box. The angles of the prism are 45, 45 and 90 degrees. This is a device used to view objects that are behind a wall. The incident ray of light undergoes total internal reflection in the prisms. On figure 6.1, complete the path of the ray through the device and show the ray as it emerges from the box. Since this is total internal reflection inside prism, that means angle of incidence and reflection are going to be 45 degrees. And that means the refracted ray is going to be perpendicular to the incident ray. Incident ray over here continues until, alright, since this ray is perpendicular to the normal of the two medium over here, the two media over here are the air and then the prism, and both of them have a normal perpendicular to the border, which is, as you can see over here, this one. And so because they are perpendicular to each other, that means the incident ray is going to go through state, it's not going to bend. So it goes through state through this line, but over here we have a normal. As you can see over here, this angle of incidence is not 90 degrees, which means a total internal reflection is going to be occurring over here, as it is mentioned in the question, I think. So it bends by 45 degrees and goes straight over here. Once again, over here, the incident ray is just along the normal of both of the media over here, which is air and the prism. This is the normal and they are parallel to each other, and that means no bending. But once again, over here, the ray bends and goes to the eye. P. Show that the refractive index of glass with critical angle is of 45 degrees is 1.41. Alright. So refractive index is equal to 1 divided by sine critical angle. And so that should mean the refractive index should be 1 over sine into critical angle, which is 45, which is 1.41, just the figure given in the question. 7a. A student makes a transformer that uses an alternating current supply with an electromotive force of 12 volts to induce an output potential difference of 2 volts. The student is provided with 2 lengths of insulated wire and the U-shaped piece of iron shown in figure 7.1. Complete and label figure 7.1 to show the transformer connected to the supply and the output of the transformer. Alright. As given in the question, the input voltage is 12 volts, which means the number of turns on the primary coil on this side is going to be greater than the secondary coil, which produces an output voltage which is much lower than 12 volts. And that means this is a step down transformer, which means the amount decreases from 12 to 2. And so we should draw the number of turns accordingly. So the primary coil has greatest number of turns. So here I have my coil and it is connected to an AC supply of 12 volts, and then I'll label this primary coil. So the output is of 2 volts, which means the number of coils over here is going to be less. I'll just draw 3 of these, and you can put any output over here. I'll just name it the secondary coil. To explain the function of the piece of the iron in the transformer. Alright, so here we're supposed to be mentioning why we're using the iron, and as also the reason of using this shape of iron. So the iron is a good conductor. Oh, and the second reason is the shape of the U-shaped magnet, and because of this, once magnetism is induced in the primary coil, it links with the secondary coil, and that helps for the EMF induction. Three, the output of the transformer is connected to a lamp. The current in the lamp is 100 milliamperes. The transformer is 100% efficient. Calculate the input current to the transformer. I'll start by converting 100 milliamperes to amperes, and that is 0.1 ampere. Since dividing it by 1000. So we'll be using the formula V1 over the second current is equal to V2 by the first current. So this one is the voltage in primary coil, this one is voltage in secondary coil. Similarly, this is current in primary coil and this is current in secondary coil. Since over here we're supposed to be calculating the input current, which means current in the primary coil, this is going to be equal to voltage in secondary coil multiplied by current in secondary coil divided by voltage in primary coil. And that means 0.1 into 2 divided by current voltage in primary coil, which was 12, and this gives the answer as 0.0166. So I'll round it to two significant figures, which is 0.017 amperes. D, another transformer is used in a school laboratory to step down a main supply of a potential difference 110 volts to 12 volts. This transformer is mounted in a metal case. State and explain an essential safety feature required for this arrangement. Since over here this is a metal case, this means this should be earth connected to the earth with an earth wire to prevent any sort of electrocution in case the live metal wire comes off and gets in contact with the metal case. If it did, that would mean any student touching the metal case without the metal case being earthed would be in danger of being electrocuted. So here we need to earth it. 8a, a light emitting diode is a diode that emits light when there is a current in it. Draw a circuit diagram showing an LED connected so that it is lit in series with a battery and a fixed resistor. Use standard electrical symbols. Right. So first off, we have a battery, which means with multiple cells, and then we have an LED connected in the right direction, which means positive terminal connected to the positive side of the battery. Right, so here is my LED, and then a fixed resistor. B. The potential difference across the LED when lit is 3.1 volts and the current in the LED is 0.30 amperes. Calculate the value of resistance of the LED when it is lit. So resistance is voltage divided by current, which is 3.1 over 0.03, and that means resistance is equal to 100 ohms. See figure 8.1 shows a power supply of EMF 150 volts connected in series with a lamp and a heater. The potential difference across the lamp is 2.1 volts and the current in the lamp is 1.5 amperes. Calculating the resistance in the heater means resistance is equal to voltage over current. Since this is a series circuit, that means the current in all of the appliances is going to be 1.5, the same, and voltage over here, however, is going to be divided, which means the voltage in heater is going to be total voltage minus the voltage which is already being used in the lamp is 2.1, and that is equal to 8.4. So resistance of the heater is going to be equal to 8.4 divided by 1.5, which is the current, and that means 5.6 ohms is the resistance of the heater. 2. The power of the heater. So power is voltage into current, which is 8.4 into 1.5, and that is equal to 12.6 watts of power. 9a. Complete the truth table shown in table 9.1 for an AND gate. NAND gate means the outputs are going to be exact opposite of an AND gate. So an AND gate would only have had the output as 1 in case of both of the inputs being 1. However, in the NAND gate, that should mean the only output which is not 1 should be the last case. That means the last case would have the answer as 0 and the rest would be 1. B. The circuit shown in figure 9.1 contains two different types of gate labeled X and Y. Table 9.2 shows a partially completed truth table for this circuit. 1 from table 9.2 deduce the name of the logic gate Y. Alright, so here we have the logic gate Y and it has the inputs A and B and the output is D. So as you can see over here, the only output which is 1 over here for D is when it has both of the inputs as 1, which means this gate Y over here is an AND gate. And so I'm going to be circling AND to complete the truth table in table 9.2. So we need to have the outputs of E. Alright, so E has the logic gate X, which means this X over here and X over here are the same logic gates. And as you can see, the results of C from the inputs of A and B indicate that logic gate X is an OR gate since it has the outputs as 1 when at least one of the inputs has 1. And that should mean E is also an OR gate. So we have 0, 0 give 0 in an OR gate, and the rest of the three cases have the output as 1. C. There is a current of 3 amperes in a copper wire. Calculate how many electrons pass through the copper wire every 60 seconds. The charge on an electron is 1.6 into 10 to the power of negative 19 coulombs. Alright, so charge is equal to current into time. Over here, the charge on a single electron I'll write over here charge on one electron is given, which is 1.6 into 10 to the power of 19. And this is charge, so I'll write the symbol of charge over here. And now this wants the total number of electrons. So here we are given with a scale, which means to figure out one of these two values, we need to have the second one of them. If they are asking the number of electrons, that means we should have, for those number of electrons, we should have their charge. And so charge here is going to be equal to current into time, which is 3 amperes multiplied by the time taken, which is 60, and that gives the answer as 180 coulombs. I'll just write the capital C over here. Since one electron has the charge of 1.6 into 10 to the power of negative 19 coulombs of charge, how many electrons have the charge of 180 coulombs? So x over here is going to be equal to 180 divided by 1.6 into 10 to the power of negative 19. Alright, this is a 19 over here. It seemed like a 14 previously. So this is equal to 1.125 into 10 to the power of 21 number of electrons. So I'll convert it to two significant figures, which is 1.1 into 10 to the power of 21 electrons. Then figure 10.1 shows a vacuum tube with a radioactive source. The radioactive source emits alpha particles, beta particles, and gamma rays. There is a very strong magnetic field between the north pole and the south pole of the magnet. The lead cylinder has a narrow central hole. State and explain the effect of the lead cylinder. Since lead cylinder is impenetrable by most of the radiations, that should mean that it would absorb most of the radiations, and it would only allow the circle over here, which does not have lead, means that it would direct all of the radiations in one direction. So the lead cylinder over here gives direction. B. Describe the paths of alpha particles, beta particles, and gamma rays as they pass through the magnetic field. Explain your answers. So the paths depend on their charges. Using the Fleming's left-hand rule, the first finger you should start by having all of your fingers being perpendicular to each other, which means your thumb, your pointer finger, and your middle finger being perpendicular to each other. The pointer finger indicates the poles, the magnetic field, which is from north to south, and that should mean your first finger should be indicating downwards, since this is from north to south, and then your middle finger indicates the charge, the direction of the conventional current, since conventional current is also the direction of positive charges. And over here we're first starting with the alpha particles. They also have positive charge, and that should mean they have the same direction as conventional current. So your middle finger should be pointing from right to left, with your pointer finger pointing from upward to downward, since this is north to south. And that should mean your thumb would be, if you're using it the right way, your thumb would be pointing towards you. And so that means the deflection of alpha particles is going to be out of the page or towards yourself, because alpha particles over here are equal to the conventional current. Now beta particles have the opposite charge of alpha particles, that is negative charge, and that means the only change over here is going to be the position of your middle finger. So the first finger, your pointer finger, is going to be pointing again from up to down, upwards to downwards, north to south. The middle finger is going to be pointing in the opposite direction, which means left to right, since here we have not conventional current but a direction of beta particles which have the opposite charge. And so your thumb should now be pointing towards and into the page. So here I have my direction as into the page. And the reason is that it is the same as conventional current in the opposite direction, because they have the opposite charges. Three, gamma rays. So gamma rays do not have any charge, which means they would not be affected by magnetic field. The path over here is it's going to go straight. And the reason is that it has no charge, which means no effect of magnetic field. Alright, so we are done with this paper. Thank you for watching.